Hi there and welcome back again. From graph processing to regular expression matching to something entirely different. And this time it's Sudoku solving. Greetings. Now for an entirely different example. As you will see, it starts out with Sudoku, but it ends up with recursive array processing. So we are continuing our exploration of using recursion in SQL to solve a multitude of problems. Okay, so you all know Sudoku, I guess. Well, it's all about these 81 cells that have been arranged in this square shape, and in each row, and in each column of such a shape, and in each box, this is such a box, we have to enter the digits 1 to 9, but in no row, no column, and no box, there will be any double digit. So any digit that we enter into a row, box, or column has to be unique. All right. And that's, of course, a rule that applies to every row, to every column, and to every 3 times 3 box in this Sudoku grid. Indeed, Sudoku means it's number with single status. So within your row, your column, or your box, your digit, your number, you have a unique property of being that particular decimal digit. All right. Well, this is a typical Sudoku board in the sense that some of the digits are already been given. So if you're really a professional Sudoku solver, then you can do with less digits being specified here already. There has to be a number of digits given so that it's guaranteed that this Sudoku has a unique solution. So any good Sudoku board will only admit one particular assignment of digits to these 81 cells. Indeed, this would be one such valid Sudoku board, so have a go at it. It indeed has a unique solution. All right. And as I told you, these Sudokus, they will lead us to actually recursive array processing because, as I will show you on the next slide, we will encode this Sudoku board in terms of an array. All right. One thing of note before, so I'm a big Sudoku fan, and I want to apologize to all Sudoku fans out there. What we are going to do in the coming minutes will be a generate and test brute force style algorithm that tries to fill in the valid combinations of digits into the empty fields of the Sudoku boards. This will not be about whatever, naked singles, pointing pairs, triads or quads, or X-wings, or hidden pairs, or swordfish, or any of these advanced techniques that you can use to solve Sudokus and draw lots of fun from. For such cool discussions of Sudoku boards, I can only direct you to the wonderful channel called Cracking the Cryptic that is being run by Mark Goodliff and Simon Anthony, two UK expert puzzle and Sudoku solvers. Please go there and waste your life away on their YouTube channel. It's really worth it. It's just magnificent. All right, back to our down-to-earth generate and test attempts to solve such Sudokus. As I told you, we will use an array-based encoding of these Sudoku boards, and we will use a row major array encoding. So indeed, this two-dimensional Sudoku grid structure will be transformed into a one-dimensional array structure by just walking the rows of this Sudoku grid, walking this row first, then walking the second row first, and enumerating the cells in this order into an array of length 81 cells, 81 elements, 81 integer elements actually. What we will do is we will encode empty cells in a Sudoku grid that are to be filled by us as solvers. We will encode these as 0 inside our array of 81 integers. And of course, the pre-specified, the given digits will be just encoded as themselves, as the integers 1 to 9 themselves inside our array. Okay, So given such an array, how would we talk about a particular cell in a particular row, in a particular column, or in a particular box? Well, we would of course just specify the array index in our linearized one-dimensional array. From that index, which of course will lie between 0 and 80, from that index, we will be able to derive the row, the column, and the box of this particular cell C using some, well, more clunky than elegant arithmetic, I would say. So, for example, the column of the cell C would just be the modulus by 9 here. I think that should be obvious. We can also compute the row of the cell C by just using this integer division by 9 and then the multiplication by 9. And the box, so the 3 times 3 box of which there are also 9 in a complete Sudoku grid. We can also compute the box of the cell C by using this horrific formula here. Give it some thought; it will just work out. What you will get is the upper left index of the box that contains the cell C. All right, I admit that this is somewhat clunky and hacky. There's of course other encodings of grids. We have seen some in the course and the assignments already. There will be more in the course. Let's go with this particular encoding because it leads to a one-dimensional array and gives us the opportunity to find an elegant solution, compact solution using very simple techniques. Okay. Right. So how will we go about this? How about the invariant that we have talked about so often already in our solutions to recursive problems? Well, we will build, of course, a recursive common table expression. And in this case, this recursive table expression will build a 2-column table called Sudoku. All right. The 2 columns will contain the array-based encoding of the Sudoku board in column board. Okay. And it will contain an integer called blank. Okay. This integer will either be an array index between 0 and 80, and if it is such an integer array index, it points to the leftmost 0 entry in our board encoding here. You see there are many zeros still in our board that we have encoded here on the left-hand side. The index of the leftmost of the first 0 would be found encoded as the integer b in this column blank. If there is no such 0 in this board here, in this one-dimensional array, then this means all cells of a Sudoku board have been assigned a decimal digit between 1 and 9. In this case, there would be no blank, and in this case, the b here in the blank column would be null. This is the convention that we are trying to implement here. Okay, so this already specifies the invariant that we try to maintain in the base case query Q0 and in all iterations of our recursive query, the Q loop query that we will see in a minute. All right. Because this is the brute force solution and not the Simon Anthony style elegant solution, it will be a generate and test algorithm that just uses the computational power of our database system and the computer we are sitting on to just fill in all the possible digits at the blank spot inside our Sudoku board, and will then check whether the resulting board would still be a valid board. So at the beginning, there will probably many such possibilities to fill in digits and still turn up with a valid board or a possibly valid board. As we progress and more digits are being filled in, we will probably have less degrees of freedom to fill in such digits. In the end, we will end up with a unique solution, a unique assignment of integer digits to the 81 cells inside our one-dimensional array. Okay, right. So let's look at the query again. As it has been good style in the recent videos, well, the solution fits on a single slide. There it is. Okay, I admit that I have reduced font size a bit here, but also because of well, the number of comments that I have left here. Okay, so of course we would start with our Q0 query. The Q0 query, the base case query, will compute a 2-column table just like the QLoop query down here. Okay, and of course it will be these 2 columns, the board and the blank column. We would start with an input board that somebody has specified. So in the input table, we would expect a single column board that encodes an integer array of 81 elements. Some of these elements, probably most of these elements, will be 0. This will be put into the board column just unchanged. This is the board that we are starting with. Right. The position of the leftmost 0, of the leftmost blank position, well, we can easily find that using the array position built-in function in PostgreSQL. We subtract -1 here because we are operating with 0-based array indexes to facilitate the column, row, and box computation that I've sketched on the previous slide. Okay, so this is the position of the first 0 that we will have to fill, the first blank that we will have to fill. You see that we are talking about back-based semantics here, and we can briefly sketch why this makes sense. But let's first look at the QLoop query down here. This would be the recursive query. All right. So, well, what would we do? We would look at the current state of our solution. We would look at the current state of the latest state of the Sudoku board that we have produced. This is to be found in the recursive table Sudoku here. All right. Into that last state that we have found, or the last states that we have found, we may find many in each of the iterations. Into these last states, we will try to fill in all the digits from 1 to 9. So this is truly brute force here, truly a generate and test approach to solving this Sudoku problem. This would be the generate part. This would be the generate part. Generate all the possible next board states by just trying to fill in all the integers between 1 and 9. Okay, of course we would only do this. Of course we would only do this for those boards that have indeed some spot to fill. Those boards that are already complete, whose blank is null, will not be regarded here whatsoever. So they won't be considered further, and they will contribute to the reduction of the size of our Sudoku table here. Okay. For all the boards that indeed have some blank space at position B, right? Well, what would we do? We would just check that in the entire row and in the entire column and in the entire box that contains the blank spot, there is no occurrence of the digit that we want to fill in. Fill in the digit that we are trying to fill in. It probably, or it better, does not occur in the row, column, or box of our blank spot. If it does, well, then this is a possible solution that has been generated that we have to throw away. It cannot lead to a valid solution. It would duplicate a digit in a row, column, or box. Right, so that would be the test part here. This would be the test part of the query. That would be the test part of the generate and test pair. So the entire box, column, or row would be checked of whether it already contains the digit that we want to fill in. If it does not, okay, then fill in is indeed one possible digit to fill in the blank spot as .b. So let's do that. Let's take the original board, the prefix of the original board, up to position as .b, fill in the digit that we have just found, and then append the suffix of the word, the suffix array of the board of all the spots that lie beyond SB. Here we really reap the benefits of having this one-dimensional representation of the Sudoku board. Constructing a new Sudoku board that has one particular cell filled in with this digit is super easy. We will just use array concatenation here. Okay. Of course, we would have to record the next position of the leftmost blank, and that's what we are doing here. You see that we are using the same construction of the newly filled in board. We would just use that construction here, and inside that new board we would look for the first occurrence of the 0 here, and would that use as the new index of that we enter into column blank. The first occurrence of a 0 here would be the next position, the next cell that we try to fill in the next iteration. Okay, so what you see here is of course some pseudocode or some hint only at the original code that we would need to indeed check the position in the row, column or box for the occurrence of our fill-in digit. All these details are not super interesting. You will find them over in the actual SQL code. Let me switch to there. There we go. All right, so let me scroll to the top of the file. Here is where we start. Here is where we would encode our Sudoku puzzles. It's a very simple encoding of our Sudoku puzzles here. It's a text-based encoding that works in a row by row fashion. All right, so here's the digits that would make up one particular row. You can see some sample Sudoku instances that, let me scroll to the activated one here. You can find sample instances in the sudoku.sql file that you will find in the GitHub repository. So these are 9 digits in a row, and of course these are 9 rows, all right, with given digits and empty spots that we are left to fill. Okay, so let's do that. No, I'm sorry about that. Okay, so let's do that now. All right. Okay, so that makes the puzzle that we are going to work on. So what we are doing now is, well, we will just perform our recursive Sudoku generate and test brute force computation here. Before we can do that, we use this pre-processing query here to turn the character-based puzzle. So let's have a look at the puzzle. Here's the puzzle that we've just stored. That will convert this character-based puzzle or a row-based puzzle into the row major one-dimensional array encoding that we have mentioned. And this will then be found in the single column table input board. Okay, and this is indeed what we read here in the Q0 in the base case query of our recursive common table expression. As you can see, we would just read the board here unmodified and look for the first blank position inside the board. Everything else is just what you've seen on the slides, with the sole difference that, of course, the pseudocode that has been checking for the occurrence of the digit to be filled in to the current row of the board or the current column of the board or the column box of the board. Well, this code is actually found here. What you will find here and the prefix is just our way of addressing a particular or identifying a particular box given just the position of the blank, right? Or a particular column or a particular row, and then just walk down the row or walk down the column or navigate inside the box for all 9 positions I, which of course range from 1 to 9. So all of these positions inside the row, column or box would be checked for an occurrence of the fill-in digit. Okay, we hope to not find it because this means fill-in would be 1, possible next digit to fill in into our boards. And that's what we are doing here. So you've seen that already on the slide. So there's some post-processing going on here, but let me show you the raw Sudoku board that is being constructed by this recursive computation. I could of course show you the entire Sudoku table that has been accumulated and constructed while this recursive common CTE runs, but it would be huge. So I better not do that here in this live demonstration. Have a look at it when you try this code on your own box, and you will see how the position of the blank is moving from left to right in this one-dimensional array encoding until there is no blank left anymore. So this is exactly the row that we will print here. Exactly that one row, because this Sudoku board has this unique solution, that one row that contains a null blank. So every digit has been filled. There is no blank anymore. Let's do that. Take some time because this box is busy with encoding. All right, so this would be the 81 digits in row major encoding that would have to be filled into this one particular Sudoku board. Okay, so on a lightly loaded computer, this would probably run between 500 milliseconds or something, which is okay for a brute force solution, although it's not elegant. Okay. Right, nobody can read this 81 character string, so we of course could format that particular string and have a row-based two-dimensional representation. Again, we could do just that. You will see that there is another recursive CTE here, another recursive CTE that computes the output. In this case, I have specified and formulated the transformation of this one-dimensional 81 element array into its two-dimensional representation to be represented for proper and nicely readable output. Just as the finger exercise, this also has been specified as a recursive query. Maybe you want to have a look at it just to have yet another example of recursive CTEs in SQL. So let's do that. Compute the board again, and then see the filled-in board. Indeed, that would be a valid solution that we could copy into the empty Sudoku grid that you have seen on the slide before. All right. Yeah, so much for this generate and test approach to the solving of Sudoku puzzles that led us to the recursive processing of arrays. All right. That's another use case of recursion in PostgreSQL. I hope you enjoy that. Don't forget to stop by cracking the cryptic, but don't forget to come back to the further videos in this course on uses of recursion in SQL. See you then.